Eckhard Sobrich and Herman. And I'm sure I butchered that name. But anyway, Professor Witko will be the presenter of the paper.
Thank you very much. Good morning to
Would you
everybody.
like a microphone now? That's a laser. Okay.
Well, I have to say that I am in a very comfortable situation because I do not need to do any introduction. After this extraordinary keynote lecture, we are already in the middle of molybdenum
Microphone up.
world.
Can you move up your collar here? There you go. Okay, thank you.
Well, the goal of our study is, of course, as anybody else, to understand the mechanism of catalytic reaction, especially the reaction which takes place on a molybdenum-based catalyst. Well, one can ask the question what we have to know in order to understand the mechanism of reaction. I think one has to have a knowledge, detailed knowledge of the physical and chemical properties of the surface. One has to be able to describe the transition states which is formed at the surface. And one has to be able also to characterize and select all the elementary steps of the reaction. Well, if we put all this together, we immediately see that the most important and first to study is the surface of the catalyst, because it is the surface which is responsible for the interaction with the becoming molecule. It is the surface which is responsible for the bond changes, the surface which is responsible for the interaction between adsorbed species, and last but not least for the desorption process. We know that nowadays there exist hundreds of very sophisticated experimental techniques which supplies us with information on atomic level. We can get the information, some of them I put on the folia. We can get the information on electronic structure, on geometry, topography, chemical composition, and etc., etc. Well, I think that from our experience, we can also say that in the last decade, we can use the theory as also the parallel and complementary tools to study the catalysts. Well, that is mainly due to of course, the development in the computer, but also to the development in methodology. Since this lecture is, I think, the only one in that section on the theory, I will focus a few minutes on the model. Well, at the beginning, I have to say, and aware everybody of you, that by definition, model is something which is incomplete with respect to the object which is going to be described. Well, if we construct the model, we have to do it in such a way that it not only gives the answer to the question to which it was designed, but also is able to predict some of the behavior of the system which were not stated when the model was built up. We can divide the model into two components, the geometrical model and physical and chemical model. Well, geometrical model is something very simple because it's just a portion of matter which we are going to describe. A little more difficult is the physical or chemical model, but one can say that there are just all kinds of forces which operate among the atoms in geometrical model, but also all kinds of mathematical assumptions which we are doing in order to describe these forces in the mathematical way and to solve the Schrödinger equation. The quality of the results which we are getting after the calculation depends on both of these components, so it depends on all kinds of manipulation we are doing to these components. As far as the surface is concerned, we are having two possible models. We can deal with cluster model or with slab bulk model. Cluster model assumes the localized interactions near the atom in the active center. That means that we can cut out from the surface some portion or some portion of the bulk and treat it as a molecule, fictitious molecule, so we can also add to this molecule adsorbate species like a ligand, and such a fictitious molecules with or without boundary condition, it doesn't matter now, can be treated by the standard quantum chemical models. Cluster can be chosen with different sizes, different geometries, different electronic states, but the main drawbacks of this approach is the fact that the atoms at cluster periphery are treated incorrectly. Therefore, the results depends on the cluster size and geometry. Therefore, at this point, I must say I do not agree with our plenary speaker today, because I think whenever one works with cluster, one should start with a small cluster and enlarge it to the point in which we are sure that the electronic properties of the cluster do not change. The second model is slab bulk model, which relies on the periodic assumption of all atoms and molecules at the surface, and the system is just described as a surface slab, which for the computational convenience is repeated perpendicularly to the surface with vacuum separating and forms the three-dimensional system. Such a three-dimensional system are treated by the standard solid-state method. Well, the requirement of the periodic arrangement of all atoms means in particular that in the case of adsorption, we can arrive at a situation where the adsorbate molecules are very close to each other. Therefore, we can have the artificially strong interaction between them. So, for example, if we really want to describe the adsorption of a single molecule, we have enlarged the supercell. That, of course, means more computational effort, and again, we have to make some kind of balance. Therefore, we see that these two models really describe the reality from the opposite direction, and in order to get the full picture, one has to make parallel approach with these two methods in the same time. As far as the physical or chemical model is concerned, we can have two approaches: ab initio approach or semi-empirical approach. Ab initio approach means that we do not use any empirical parameter nor fitting parameters. We are treating all electrons, and we can proceed either through the Hartree-Fock scheme or very fashioned now density functional scheme. We are getting very highly accurate electronic states, potential energy with all the characteristic point, minima, maxima, saddle point. The problem is that we are still doing with this approach with a relatively small models. However, frankly speaking, the small models are becoming larger and larger from year to year. In the semi-empirical treatment, we treat only the valence electron, which is nothing bad because this electron really takes part in the chemical reaction. We proceed only through the Hartree-Fock scheme, and we are getting on the quantitative trends, but for very large systems, which are usually 2 orders of magnitude bigger than in the case of ab initio treatment. Well, the results which I am going to present today will be the results of cluster approach and density functional theory, so there are some details for those who are interested in. I just want to point out that we have selected very big cluster, like molybdenum-15, oxygen 56 in the case of molybdenum trioxide and molybdenum 17O32 in the case of molybdenum dioxide, after studying the electronic properties of this system. What we can get from the quantum chemical calculation? Well, we can get a set of electronic structure parameters. Some of them, which I will be discussed today, are listed on this folio. First, we can get, for example, the electronic charge distribution. That means we can get the atomic charges, and immediately from that we can say about the ionic contribution to the bond. We can also have some information about the covalent contribution of bond to the total bond just by studying the bond orders. The bond orders can be also used as a measure of the bond strength. These two, however, parameters cannot be compared to the experiment. The next set of the parameters can be compared with the experiment, and we can, for example, discuss all kinds of the energetics. We can look for the absorption energy, for the activation energy. However, this task is extremely time-consuming and difficult. We can also look for the total density of states and compare it with the UPS spectra, for example. And we can supply the experiment with the additional information and help in the interpretation by making the projected partial density of states. And of course, we can discuss the bond orders and bond distances. Let me go to the system which I will discuss today, the molybdenum trioxide and molybdenum dioxide. Molybdenum trioxide has the orthorhombic lattice. It is a bilayer structure. These two bilayers are connected within each cell by very weak forces, like one can say van der Waals forces. And the building unit is very distorted octahedron with the distances, MO distances varying from 1.6 up to 2.3. In contrast, molybdenum dioxide as a monoclinic lattice, the MO distances are very similar. The difference is only 0.1 angstrom. It does not have any layer structure. What is interesting in these two systems is the different kind of oxygen one can meet in. We can have the singly coordinated oxygen, which will be denoted through all my talk in Z. We can have a doubly coordinated oxygen, very asymmetric in the case of molybdenum trioxide, and very symmetric in the case of molybdenum dioxide. And we can have, which will be blue, and we can have a triply coordinated oxygen, which will be always green. In addition, in the case of molybdenum dioxide, when we cut the surface, we can meet the molybdenum, which are fifth coordinated, and we have still the molybdenum, which has the coordination number equal 6. If we go now to the more detail, we have here the pictures for molybdenum trioxide 010 plane. We see that it's built on the rows of MoO octahedra, which are linked by edges, by corners. And there's the cluster we have selected, this bilayer cluster, and these pictures show you the way we have cut it out of the bulk. The same pictures for the molybdenum dioxide looks in that way. We have selected to our study 010 surface, again the row of molybdenum oxygen octahedra, where the octahedra in the row are linked via edges and between the row via corners. Every second row is tilted by 90 degrees. Here I have also show you the cluster which we have selected, and that is in fact, very clever cluster, because we can describe molybdenum which is fifth coordinated. This is when we pick it up from here, or molybdenum which is sixth coordinated here when we pick it from here. So one has only to turn upside down the same cluster. Now, of course, will come some numbers. Let's start with discussing the electronic structure of these two systems. What I would like to point out is first that the atomic charges are far from the formal oxygen charges. We are getting molybdenum plus 2.2 or plus 1.6 approximately in the case of MoO2. The second point, which is very important, is that the difference between molybdenum plus in molybdenum trioxide and dioxide is not 2, but is about 0.7. So this means immediately that both systems are not the pure ionic systems, but has a great covalent contribution. The second point, which is also very important, is that differently coordinated oxygen are differently charged. And the charging scales with the coordination number, so the most nucleophilic oxygen is the oxygen which is triply coordinated in both cases. We can also discuss the strength of the bond. For example, in the case of molybdenum bond, this bond, which is very short, is something between the single and double bond, 1.5. In the case of bridging oxygen, very asymmetric oxygen, we have one bond which is about single bond, and the second which is very weak one, in contrast to this bond in molybdenum dioxide, where we have almost two single bonds. And we have these three very weak bonds which bonded the oxygen triply coordinated. Let us now see how we can get more information. And these are the total density of states for molybdenum trioxide. And we can compare also this result with experiment. First of all, the width of the spectrum is about 6.3, which compared quite well to the experimental data, about 7. And we have three main peaks at 1.9, 3.6, and 5.6 electronvolts, which compared to the experimental value, extremely good. This peak is artificial peak, which comes from the fact that we saturate our cluster with hydrogen atom. These are unoccupied orbitals of molybdenum. This is, of course, the Fermi level. So we see that we have the isolator, the gap is about 1.8, which in comparison to the experimental value, which is depending on the paper, but something about 2. If we compare now the density of states for the molybdenum trioxide and molybdenum dioxide, we see that we are occupying the molybdenum level, so we are going from isolator to the metal-like system. Well, the next point I would like to discuss is the formation of oxygen vacancy at the molybdenum trioxide system. Well, we all know that these vacancies are always present at the surface, and they are, because of several reasons, they can also lead to the quite big rearrangement of the surface. Therefore, we have decided to study this phenomena by taking out oxygen, singly coordinated or doubly coordinated or triply coordinated, and by allowing the whole cluster to relax after such operation. And here are the results, the geometrical results of this calculation. Let's start with the easiest example, which is the formation of oxygen vacancy by taking off the oxygen, which is triply coordinated. We see that the surface does not really feel this formation of this vacancy. The distances, the MO distances, are very similar to the distances which we have in cluster without the vacancy. In contrast to this, if we make the vacancy either by taking O1 or O2, then we end up in both cases with the same system where the second remaining oxygen takes geometry between these two. And we can see that it gives the distances very similar, 1.6 or 1. Almost the same, which are very similar to the molybdenum distances. In fact, if we go to the electronic structure for these cases, we also see that this remaining oxygen takes also the charge 0.4, like it was in the molybdenum oxygen. So the formation of O1 or O2 vacancy caused a big rearrangement of the surface, and the remaining oxygen behaves like the molybdenum oxygen, except that it's just a little bit tilted towards the surface. We can see also the formation of this oxygen vacancy by plotting the total density of states, and we see that the vacancy formation leads to the reduction of molybdenum, and we are getting the additional molybdenum peak over here. In fact, maybe it's even better to see it on the next folia, where we have show the reduction of molybdenum. Here I have colored the atomic density of states which come from the molybdenum. We start with the isolator. By making the oxygen vacancy, we are reducing the molybdenum, forming this additional peak, and we are going to the metallic-like character in the case of MoO2. In fact, this corresponds very well to the experimental data which we have obtained from the Fritz Haber Institute, from the Dr. Messel, which I should thank him, where they start from the molybdenum trioxide. This is the peak for molybdenum trioxide, and they got this additional peak up to the molybdenum dioxide with this 2 peak. We can even try to put our results together, and for example, you see this corresponds very well, this additional peaks to this, what we are getting from our calculations. Well, we have also studied the very simple surface reaction, which is the adsorption of hydrogen by absorbing hydrogen on different type of oxygen, or 2 atoms. In both cases, hydrogen is stabilized at the surface and forms the hydroxyl or surface water species. Well, I will not go into details of these studies. The only thing I would like to show you is just the geometries of this surface species. The most interesting point with these geometries is the case where we adsorb the hydrogen on the triply coordinated oxygen, because the OH group, and the same is true for water molecule, one of the hydrogen is going below the surface, and we believe it's the beginning of the formation of molybdenum bronzes. Well, going back to the oxygen vacancy formation, we can ask ourselves how difficult it is to make such a vacancy. Well, it's extremely difficult because the oxygen is very strongly bonded to the surface, about 7 electron volts, which is a lot. But we can think about the following trick. First, we make the surface hydroxyl group or surface water group, and then try to remove this species. And we see that in each column, hydrogen assisted the formation of the vacancy, and the energy is almost half of the energy without the hydrogen. And the third point is that the lowest energy, so the easiest place to make the vacancy is the triply coordinated oxygen. So let me summarize what we have learned from this calculation. I hope I also convince you that the theory can give some additional input to the experimental data. We have learned that both systems are the system of the mixed ionic and covalent natures, that differently coordinated oxygen are differently charged. The charging is scales with the coordination number. The most nucleophilic species is triply coordinated oxygen. We have learned that hydrogen can stabilize at all oxygen and leads to the stable hydroxyl or water surface species. And oxygens are extremely strongly bonded to the surface, but hydrogen present may facilitate the removal of surface oxygen. Thank you very much for your attention.
Thank you, Professor Witko. Are there any questions? Yes.
With such large clusters, it's quite difficult to get the spin state of the cluster correct.
Excuse me?
With such large clusters, it's quite difficult to get the spin state of the cluster correct. How do you address that?
Well, we have selected we have studied different spins of these clusters, and we have selected the ground spin according to the lowest total energy. In fact, in molybdenum trioxide, it's not a problem. In molybdenum dioxide, we are always dealing with a triplet state, not a singlet state, but I think that's okay.
Yes.
I have a question about the geometry of the oxygen-1 vacancy calculation. It looked like the MoO3 distance on your slide was 4 angstroms.
Yeah, because...
Discuss that?
Sure. This is because this oxygen, where is it? This is because this oxygen, which are, for example, which was here, and have 2.2 distance to that molybdenum, when it's tilted upside, that distance is getting 4 instead of 2. But that distance, which was 1.7, now it's shorter.
One more question.
Yeah.
Because when you do DFT, we always assume those states are for non-mechanical system. But for a real system, I mean, we always have some real electron intelligence. I don't know how in what sense you would expect those two things will match each other. Basically, it's not, I don't have a visual picture of why people would like to compare. I don't know. It just seems so.
Well, friendly speaking, you can make the density of states really from the solid state physics approach. That is sure. But then if you are also doing a very large cluster like we do, the dense of the molecular orbital is such a big one, so we can treat the spectrum as a continuous one spectrum.
No, I actually don't think. I mean, what I mean is those potential states of DFT configurations are for independent particle combinations.
Yeah.
Those are for non-independent.
Well, with all this assumption, as I told you at the beginning, it's just model, and we know about all this limitation of the model. We have to accept this limitation.
Okay, thank you.